Let me welcome you all to our first Inspiration Exchange session of 2024 on double descent and ensemble learning. And I'm delighted to welcome you to today's session, where we'll be joined first by two speakers from our lab, PhD students Alan Jeffares and Alicia Curth, who will be covering the topics of both double descent and ensemble learning through a couple of presentations, including an introduction introducing everybody to these topics, which might be more unfamiliar than some of our usual topics covered in these sessions. In the second part of today's session, I'm delighted to be joined by two guests from industries for a roundtable discussion and a Q&A session. And I'll introduce our guests more formally later during the session. If you've got questions for any of our speakers or panelists, as always, please do ask them in the Slack channel, and I will post the link to join Slack if you're not already on it in a second in the chat. Before we kick off today's session with an introduction on these topics from Alan, I'm just going to hand over to Professor van der Schaar for a brief welcome from her as well.
Thank you very much, Fergus. I wanted just to wish everyone a very happy new year. And I also wanted to wish you a lot of inspiration and excitement for the area of machine learning. Thank you for being with us today. And I'm delighted to see these sessions continuing to provide interactions between our lab and many of you. And I'm especially excited to be starting the new year with the topic of machine learning theory and deep learning theory. So very often in our sessions in Inspiration Exchange, we think about novel cutting-edge machine learning techniques that are, of course, very important if it is to make the world of reality-centric AI become really developing and becoming part of the reality of AI. But what's also very important is to be realizing that the foundations of machine learning are important as well if it is to build reality-centric AI. So what's wonderful today is to have Alicia and Alan introducing you to this field and bringing you to an exciting set of works that they've been doing in the last couple of years. And what I'm also excited to say is that later in February and March, we are going to go totally on the other side and talk about large language models and foundational models and how they can inspire us. So going all the way from theory to the cutting edge of foundational models and large language models in the beginning part of this year. And we hope that you are going to join us in many of these sessions. Thank you.
Yeah, so I want to just set a little bit of context before we dived into the details of the papers. So this is, yeah, as Mihaela said, a little bit more on the fundamental method side than some of these sessions typically are. So we kind of wanted to give some context of how we ended up in this kind of rabbit hole of these two papers and what led us there. So this work was kind of kicked off back from an iClear 2023 paper, which was called Tangos. And in this paper, we were actually originally, it was more of an applied problem. We were looking at improving deep neural networks on tabular data, which is kind of a modality that they've kind of struggled on historically. And in doing that, in kind of training neural networks on tabular data, like a natural baseline there is ensemble learning, with all the state-of-the-art methods on tabular data being gradient boosted trees and random forests and this sort of thing. So we were thinking in terms of ensembling there, and that led us to this method called Tangos, which was a regularization approach for deep neural networks. But it kind of, the motivation was to make the neural networks behave a little bit more like ensembles, to encourage diversity on them. But I guess that kind of got us thinking a little bit, and I should say that paper was with Tennyson Liu and Jonathan Krabbe as well, and Fergus, who's on the call, and obviously led by Mihaela. And then, yeah, that got us thinking a little bit more about ensembles more generally. So at NeurIPS this year, 2023, we had a paper called The Joint Training of Deep Ensembles Fails Due to Learner Collusion. And here we'll get into the details of the paper, but the idea was then we started looking at how deep ensembles are trained, so how ensemble methods are trained in this kind of new neural network regime. And that's going to be part 2 of this presentation. So it's a little bit revert. So the chronological, we're not going to follow exactly chronological order. And then before that, the subsequent paper is a U-turn on double descent. This was an oral from Europe this year, and this was with Alicia Curth. And in this paper, then we were following on from the joint ensemble paper, which got us thinking about model complexity and how if scaling models in terms of adding ensemble members is kind of like other forms of scaling, which got us thinking about double descent, which is a phenomenon we'll get into. And yeah, so naturally from ensembles, we started thinking about increased complexity, and that led us to finding some interesting things on double descent. And then very briefly on future work, there's kind of 2 directions we're following up here. So we're hoping to have preprints released for both these papers this month. So one of them is kind of taking a deeper dive into why random forest works and how they're distinct from kind of deep neural networks and this sort of thing. And then another paper, which is kind of trying to find ways of making deep ensembles train more efficiently. So a big observation that we'll find in the joint training paper was that deep ensembles are actually pretty inefficient to train. So we're going to start with part 1 with a U-turn on double descent, and this was joint work with Alicia. So we're going to co-present that. I'll do the first half, and Alicia will take the second half. And then following that, we're going to move on to the joint training deep ensembles paper, where I'll join and talk through that work. So let me just set up my screen here. So yeah, so this is a U-turn on double descent, rethinking parameter counting in statistical learning. And this was joint, as I said, this was joint work with Alicia Curth and supervised by Mihaela van der Schaar. So every introductory machine learning class begins by describing the relationship between model size and test error as having a U-shaped curve. The general idea of this curve is that we fit a model to a fixed data set, and as model complexity increases on the x-axis, typically measured by the model's parameter count, prediction performance measured on a test set displays a distinctive U-shape. At first, performance improves as the added flexibility is better able to model the complexity of the underlying process, and then performance worsens as the model reaches sufficient parameters to overfit to the training data. However, recent work has argued that this theory is generally incomplete, and as we further increase model complexity, performance begins to improve again, resulting in a phenomenon dubbed double descent. So the prototypical double descent shape begins with the classic U-shaped regime, but then reaches the interpolation threshold, which is the point in which the number of model parameters matches the number of training examples, resulting in models that interpolate the training data and thereby achieve perfect training performance. At this point, we begin a second descent, which is argued to be a consequence of entering this interpolation regime. The idea is that in this regime, models interpolate the training data as they achieve 0 training loss, but again start to achieve better generalization as we increase model complexity. This apparent disagreement with classical statistical intuition puzzled us. So in this work, we set out to better understand double descent as a phenomenon. In the first part of our paper, we revisit the 3 non-deep learning examples of double descent as presented in the seminal work on double descent of Belkin et al. 2019, where we show that simple theory can be used to better understand this phenomenon. Sorry, I'm having some trouble with the clicker. We begin with their decision tree experiment, as it's the most straightforward to understand the root cause of the second descent. This is because in this case, parameters were incremented by first increasing the number of terminal nodes in the tree, and then, from the interpolation threshold where no further terminal nodes can be added, this is changed to instead increasing the number of decision trees to form an ensemble. Thus, there are 2 distinct parameter increasing mechanisms, and only by applying them sequentially do we obtain the double descent shape. Actually, this is really a random forest with 2 hyperparameters. And if instead of increasing them separately while keeping the other, if instead of incrementing them sequentially, we increment them separately while keeping the other fixed, We recover the standard convex shapes as illustrated by the lighter dashed lines. This also highlights that the choice of switching mechanisms at exactly the interpolation threshold is somewhat arbitrary. We'll discover that such a decomposition into two distinct axes can be found in all examples of double descent that we consider. Their second experiment, which shows double descent in boosting, is very similar. But in this case, the two parameter axes are given by first increasing the number of boosting rounds of a single boosted tree, followed by, again, the addition of more independent trees to form an ensemble. Only by applying the two consecutively does double descent arise. The resolution to their third and final non-deep example of double descent, which is in linear regression, is less obvious. This experiment is set up such that the parameters are increased consistently by adding new random Fourier features, with no clear change in mechanism. However, because the problem becomes underdetermined at the interpolation threshold, the model subtly changes to selecting the min-norm solution from that point. To understand the consequences of this, note that when there are less parameters than samples, we are simply fitting a p-dimensional regression coefficient using ordinary least squares. When there are more than n parameters, we show that the min-norm solution has a dimensionality reducing effect. We show that it can be better understood as a two-step process that first learns an n-dimensional basis in an unsupervised pre-processing step, and then learns an n, not p, dimensional regression coefficient. We note that this whole procedure can be seen as a special case of a general principal components regression setup. The min-norm solution is principal components regression using all empirical principal components, while removing n minus p excess features. But it would also be possible to use fewer principal components. A general principal components regression procedure consists of an unsupervised dimensionality reduction step, which removes the excess dimensions, and then performs ordinary least squares on the reduced basis in a supervised step. We've now arrived at a setup that parallels the first two case studies. We've shown that there are two types of parameters here too: the number of principal components used in the supervised step and the number of excess features used to construct the basis. We could also vary the two separately, and have thus established that we can decompose this setting into two distinct parameter axes, where only transitioning across the two causes double descent. As double descent only arises by connecting the two solid lines across these two axes, we could also move the second descent away from the interpolation threshold. We could change the mechanism of parameter increase earlier, thereby moving the peak to the left or even fully removing it. In addition to moving the single peak, we could also create multiple descents by changing the mechanism of parameter increase multiple times, creating peaks both before and after the interpolation threshold.
So thank you, Alan, for the first part. And let me start by intuitively summarizing what Alan has told you about double descent so far. We've shown that in all three case studies, there are actually two distinct complexity axes, and that double descent arises as a direct consequence of transitioning between these two axes. A second peak occurs exactly and only when and where transition between these two axes occurs. So far, we've thus highlighted to you that not all ways of increasing the total number of parameters in a model should be expected to have the same effect. But coming to this conclusion by reasoning about implicit complexity axes isn't quite as easy as it may seem, as modern machine learning methods could have many different types of complexity axes implied by different hyperparameters, inductive biases, optimization methods. So ideally, we would like to quantify the implied complexity instead, which is exactly what we're going to do in the second part. Some previous work has indeed attempted to redefine what goes on the x-axis of these double descent plots for the same reasons, but none of their complexity measures can explain these three case studies of double descent we consider here. Instead, we therefore went back to our statistics textbooks to come up with a new perspective using some older ideas. In our paper, we noted that all three methods can actually be interpreted as smoothers, which is really useful in this context because this class of methods already comes with so-called effective parameter measures. So before we move on and dive into it, let's quickly recall from our statistics classes what smoothers are. Smoothers are a class of methods in which the predicted labels can be expressed as a linear combination of the training labels. That is, predictions can be expressed directly as a function of the training labels multiplied by smoother weights, which depend on covariates and are fixed in linear regression or adaptive or learned in tree-based methods. The distribution of these smoother weights is what determines the implied complexity of the smoother. Very intuitively, one could say that the less uniform these weights are, the more complex the smoother is. And some existing effective parameter measures are therefore based on the norm of this weight vector. And what we wanted to see in our paper is whether these measures could be applied to understand double descent out of the box. So let's use one of these effective parameter measures, which measures the average squared norm of the smoother weights used when issuing predictions on the training examples for the linear regression example. When we plot effective parameters against the original raw parameter axes, shown by the orange line here, we find that this measure saturates and stays constant once interpolation is achieved. This supports some of our findings from the first part. There's clearly something that changes at the interpolation threshold. But this effective parameter measure also does not track the double descent curve itself. We realized that this is because existing measures capture the effective parameters used when issuing predictions on the training data, as historically much of this literature has focused on in-sample prediction, while nowadays we typically study generalization to unseen inputs. To resolve this limitation, we proposed an extension of the effective parameter measure that can account for unseen inputs too. Now, as illustrated with the green line shown here, when measuring the effective parameters used for issuing predictions on unseen test inputs in this way, we can now track the model's test time complexity against the original raw parameter axes. And this does appear to track the double descent phenomenon and generalization error. Interestingly, we thus observe that after the interpolation thresholds, adding new raw parameters actually decreases and not increases the effective parameters used. Equipped with this test time effective parameter measure, we can now attempt to replot the original double descent curves on a new x-axis. We find that the curves in this way indeed fold back into a shape that more closely resembles the original U-shapes, as points after the interpolation threshold indeed use less effective parameters than those just before. You might, however, say, well, that's not exactly U-curves just yet, but that's just because the full U-shapes become more obvious when we add contour lines, representing a reduction of parameters along the first of the two parameter axes, so tree depth boosting rounds in the use principal components. And then it really becomes clear that what we've been observing is actually transitions across multiple stacked U-curves. In conclusion, with everything we've established so far, we can provide a satisfying resolution to the double descent phenomenon outside deep learning. In the first part, we showed to you that the double descent curve is best understood as being the result of parameters being increased sequentially along two distinct complexity axes, which can be unfolded to produce a double descent curve in the total number of parameters only along a composite axis. In the second part, we then showed that by measuring complexity more appropriately using effective parameter measures adapted from the smoothing literature on the x-axis, we observe a full U-turn on the double descent curve as the two axes fold back into themselves, resulting in a traditional U-shaped complexity curve. As such, we've presented a resolution to the ostensible tension between double descent and traditional statistical intuition. But before I leave you with that, let's talk about takeaways of our paper that go beyond just the double descent phenomenon. First, and maybe most importantly to us personally, we've provided some evidence that modern machine learning does not actually defy the statistical intuition we are taught in our statistics textbooks and classes. There's really nothing truly magical about modern machine learning once you have a close look at what's actually happening. And we can and should attempt to rebuild statistical intuition for other machine learning phenomena, as we hope that this will greatly help us in understanding success and failure modes of the large models deployed in practice today. Finally, and a little bit more practically, let's discuss some of the implications of our findings for working with the machine learning methods we have studied in practice. First, our results indicate that there are trade-offs between raw model size and the need for hyperparameter tuning. Along the first parameter axis we studied, so tree depth, boosting rounds, and the principal components, we observed that error is very sensitive. But along the second axis, bigger was always better. In fact, it seems that setting the second axis, so excess features or number of ensemble members, large enough may sometimes allow to remove the need to tune hyperparameters along the first axis altogether. But it does come at the cost of having to use much larger models. Second, we also found anecdotal evidence that the two axes that we observed in all of these methods play slightly different roles. The first of the two axes always controlled bias at train time. How well could the training data be fit? While the second axis really controlled variance at test time. Finally, our results also suggest that it may be possible to redeem classical model selection criteria that rely on parameter counts and not validation sets. So for example, archaic or base information criteria you may recall from your introductory stats classes, by considering test time effective parameter counts instead of normal raw parameter counts. In our appendix in our paper, we provided anecdotal evidence that this could be a possible fruitful avenue for future consideration, for example, by selecting the models with least effective parameters among all models with the same training error in practice. So these are just some of the insights we got in terms of practical implications from our paper. We hope to explore many of these ideas in future work. And in fact, as Alan was just saying, random forests are the first of these methods that we're considering in more depth, hopefully with some results out soon. So thank you very much for your attention for this paper. And I'm going to pass it back to Alan now to talk about deep ensembles instead of random forests.
So now we're kind of moving back in time to the work that motivated that paper, where we were looking at the joint training of deep ensembles. So this is previously we were looking at random forests and boosting and these independently trained ensembles, and now we're going to move into the deep learning regime where we're training multiple neural networks. And this was work with Tennyson Liu, Jonathan Krabbe, and Mihaela van der Schaar. And I should say that the title is The Joint Training of Deep Ensembles Fails Due to Learner Collusion. So yeah, so in this work, we're interested in the optimization of deep ensembles, which is illustrated on this slide, where the top indicates the inputs and the bottom indicates the outputs. And in this case, we have an ensemble of size 3. Typically, ensembles are trained by calculating the loss for each of the ensemble members using some loss function denoted by L here. And each loss is calculated independently for each ensemble member. So we take each ensemble member and we calculate the loss. This can be expressed as the following objective function. And the point to note here is that once the ensemble is trained, we no longer evaluate each of the ensemble members individually, we ensemble them jointly. We are interested in this second objective, which is the true objective, or as we refer to it, the joint objective. And the difference between these two objectives is subtle, but one is the objective of each of the individual members averaged, while the other is the loss of the average of the predictions. And this second objective is the true objective of interest in some sense, as this is the objective we evaluate on the test set. This is what if we deploy this model, this is the objective that matters. So in this work, the question we seek to answer is, why, if we're interested in this right-hand side objective, do we optimize the left-hand side objective instead? And what happens if we instead optimize this right-hand objective? And kind of the detail to note here is, yes, this individual objective on the left, where we train each member independently, made a lot of sense, when we were looking at random forests and gradient boosting, and we're dealing with decision trees, which have to be optimized independently. They can only be trained one by one. But now we're in the deep learning regime where we have, back propagation. And in principle, there's no reason why we can't just calculate the loss of the entire ensemble. So my screen seems to have frozen. Sorry, yeah. The point to note is that these two are not equal. So to really hammer this home, For each ensemble member, we take their outputs and aggregate them with some aggregation function. In this presentation, we take the mean, but in the paper, we deal with more general aggregations. And when we represent that aggregated prediction, with F bar, and we consider optimizing the loss between F bar and Y as the true objective or the joint objective. However, somewhat surprisingly, when we consider comparing these objectives on standard benchmark tasks, in this case ImageNet, using various ensemble sizes and various architectures, we consistently find that independent training results in superior performance. So this is contrary to what I expected, at least, that we find that when we optimize this, this objective that we're really interested in, the ensemble actually performs worse on the test set. So in this paper, we seek to answer the question, what is going wrong and why is this the case? So in 1994, Crow and Videlsky derived the following decomposition in the case of regression, where the ensemble error can be decomposed into the individual error and a remainder term that can always be interpreted as diversity. A similar decomposition has also been shown in the case of classification. In this work, we generalized this decomposition for any twice differentiable loss functions. That's pretty much any loss function that's used in practice. And we showed that this remainder always can be interpreted as a diversity term. So we always have this decomposition for an ensemble. We then hypothesized that the poor performance of joint training can be explained by an effect that we call learner collusion, in which multiple individual learners artificially inflate their diversity to appear diverse. Here we present an illustrative example where a subset of base learners, F1 and F2, collude in output space by shifting their predictions in opposite directions, such that the ensemble prediction F bar is unchanged, but diversity is inflated. We investigate this hypothesis. We demonstrate three effects that we would expect to see in order to investigate this hypothesis, we demonstrate three effects that we would expect to see if learner collusion is indeed occurring. So the first of these is diversity explosion. So the first of these is diversity explosion, where we show that the relative magnitude of the diversity term in the decomposition is excessive compared to the individual loss term. Then debiased diversity. The most simple form of collusion would be that each learner has a constant bias associated with their predictions. We can measure this bias and show that when learner collusion occurs, this explains a large proportion of the ensemble diversity. And then finally, learner codependence. We show that each learner becomes excessively codependent on the other ensemble members, such that randomly dropping a subset of learners at test time is catastrophic to the overall ensemble performance. We finally show that learner collusion generalizes poorly onto unseen test examples. So these were all empirical claims. So the empirical investigations with more detail is in the paper. So you can kind of see a brief overview of them there. So kind of a more fine-grained analysis. Once we've kind of shown that this learner collusion effect is indeed occurring, then we can kind of dive into a deeper analysis of, what is the effect of the outcome of this learner collusion on practical tasks. So in this case, we show the effect of smoothly interpolating between the effect of independent training on the left, where beta equals 0, and joint training on the right, where beta equals 1. And we note that as we interpolate between the two and approach joint training, test performance significantly drops. It actually drops off very sharply right as we approach the joint training on the right-hand side. We also investigate the training dynamics of ResNet models on ImageNet. So ImageNet is kind of the state-of-the-art benchmark tasks for image classification, large scale. And when we do this, we find that that on the left, independent training, and on the right, joint training, result in significantly different performance of the individual learners. On the right, we see with the green dashed lines that the individual learners perform significantly worse as their priority is on optimizing the diversity term rather than optimizing their individual performance. And this is obviously training dynamics, so over the course of epochs of training. So yeah, this has been a very brief overview of this work, and I recommend checking out the paper for kind of a complete summary of our contributions. There was a lot I kind of skipped over. Yeah, thanks very much for your attention, and I'll be happy to take any questions you might have in the Q&A.
Awesome. Thank you so much, Alan and Alicia, for those two presentations. As Alan said, if you've got any questions, please do post them in the Slack channel that I've posted in the chat. And we should have time to take some of these questions later on during the session. But before, I'm delighted to now move to our panel discussion session, and we're joined by two guests from industry. Our first guest is Dr. Dimitrios Vitzios, who is the Director of Data Science and Genomics at AstraZeneca. And we're also joined by Dr. Jeremy Voisey, who is a Senior Scientist and the Bioinformatics Team Lead in the AI Research Department at Canon Medical Research Europe.
Yeah, so thank you very much again, Dimitris and Jeremy, for being with us today. So my question will be a little bit broader than these two presentations. We have seen tremendous advance in deep learning in the last couple of years. And at the same time, it's clear that many complex problems that we are facing, and the two of you are very much involved in different areas, but very cutting edge areas in applying machine learning to very different domains. Where do you think that the theory and the science of machine learning, and in particular deep learning, could be improved to empower the type of applications that you are working on, the types of modalities that you are working on? So I wanted to ask both of you, maybe you can share a little bit about your research. I know both of you are doing unbelievably interesting research. And maybe tell us where you think that machine learning, deep learning theory can bring us forward to be able to bring these technologies further to reality in your domains and in your applications. Dimitris, maybe you want to start, and maybe you, Jeremy, next.
Yes, thank you, Mihaela. Thanks so much. I mean, for the presentations, it's amazing work really to see those papers presented, and talking about the theory of machine learning, which is not really my area of expertise, but it also aligns very well also even in the applied domain of machine learning. So just to start replying your question, Mihaela, I would probably say that usually in our domain or in applying machine learning in life sciences, we see that the value of the results comes in many cases more from the data than from the method itself. However, then we see that ensemble methods, for instance, have been very critical for the high performance of those models, and it's really probably some technical artifacts are being cancelled out between the different parts of the ensemble classifier that eventually turns out to give the correct result. So that's something that we've been noticing in our work. With regards to some more technical details, for instance, on the double descent, what I find interesting is, as an application of this paper, basically, is whether we can disentangle which types of hyperparameters per model actually are responsible for each of those axes of the double descent. Let's say, can we define them? And actually, is this bound only to just two complexity axes? Can we extend to more complexity axes? And then also another thing that I found interesting, I mean, when we add more members in an ensemble, we see that there is a decrease in the test loss. However, is this increase in the complexity similar to the increase of the parameters of a single model? Because I think these may be two subtle but different ways of increasing complexity. So I found this really intriguing and interesting, and it would be amazing if we could have even better guidance when applying our models, which kinds of hyperparameters are the most important really to to refine and fine tune. I would probably start with this.
Maybe I saw Alicia nodding. So maybe Alicia, would you like to respond a little bit, and maybe you, Aaron, but Alicia, because you got a challenge.
Yeah.
Dimitrios sent you back a challenge.
Oh, it's not so much a challenge actually, as it was indeed the entire motivation of our paper was the fact. So when we looked at the double descent in trees as it was presented in the original double descent paper, where very specifically what they did was they first increased the number of nodes in a single module, as Alan was saying, and then but like as soon as you have as many leaves as you have training examples, you can no longer increase model complexity that way. So then they had to change it. So they changed it to adding ensemble members. But it was very specifically our feeling as well. That is a very different way of increasing model complexity than adding more leaves is. So we kind of felt, well, that's not really this, it's not the same way of increasing model complexity, so why would you expect the same effect? So that's why we also started there. And then, so we took that, and then in the linear regression example, there wasn't an obvious switch. So we basically, we tried to see if in linear regression, there's like an equivalent to the leaves and ensemble members kind of decomposition, and we indeed found that. So that we very much share this feeling of it's not exactly the same way of increasing complexity. But yeah, I completely agree. Now we've looked at two, like each of these examples inherently had two hyperparameter axes, which is also why there's only one peak. But it would definitely be interesting to look at things that have more such axes and see if there's any way of kind of disentangling their role a little bit further. So yeah, right now I'm looking at random forests in a little bit more depth because I think there's some interesting stuff happening there. So hopefully that will be out within a month.
Nice.
Thank you, Alicia. Jeremy, sorry for stopping the thread, but.
Thank you both very much for these talks. Again, it's fascinating. It's nice to see people remember that classic machine learning is not being forgotten. It's still really important. I suppose we from a deep learning point of view, I suppose I'd like to see an extension of these ideas. I think I can see that was in the paper on a U-turn on double descent in the further work. Be really interested to see where you think the ideas come in there in terms of how you measure complexity with deep learning. There are many different ways to do that, of course. What would be useful to so that we don't just keep on blindly applying models. It's very often we start with doing that by where we get a model off the internet and we apply it, and we just leave it to the maybe hyperparameter selection automatic. It's great to actually have slightly more intuition. So that'd be great to extend those ideas, and I think you acknowledge already that it's not a trivial problem at all to extend that to deep learning. But the other extreme, I think it's also important to go back to tabular data. There are many applications where we're still dealing with perhaps clinical data, for example, age, BMI, blood pressure, and so on. And I'd be interested to see, for example, whether for your approaches, for example, on double descent, would actually still apply for that tabular data. My understanding is you did that with MNIST data. So I'd be interested to see does that begin to change with tabular data, or perhaps with bioinformatics data? Things like, for example, genetic mutations or transcriptomics, the RNA expression, to start to see where different data has an effect on your analysis as well.
Maybe I'll throw this question to Alan. Alan, any comments on what you have done on tabular data, and how do you think the work needs to follow through, since you have always been interested in tabular data?
Yeah, so maybe I'll start with just the point on complexity measures on deep neural networks, because I think this is a really interesting topic, and you're right, there's just a huge amount of measures out there. I think the one takeaway that kind of just came to mind when you brought that up, and I thought I should say, is that there seems to be something interesting about the interaction between the model complexity, model capacity, and the data itself. And we found that to be the missing piece in our work, that you had to account for this kind of switch from training data to testing data. And you couldn't use just like a pure VC dimension sort of measure, you know, one of like the amount of data, minimum number of data points to shatter, these sort of ideas. There has to be some accounting for the actual observed data, which is quite an interesting thing to observe. And then, yeah, on the topic of like tabular data, I think it's a really interesting area. There's a lot of work to be done. I think one thing that I've experienced is that, you know, when we give up all the inductive biases that we have, you know, in images or speech or whatever they may be, it becomes very difficult to kind of generally solve tabular data, because I think the area of tabular data seems to be kind of the everything else area, and I don't think that's I think that kind of makes things harder than they necessarily have to be. So I think if within tabular data we can find kind of sub modalities, maybe that, you know, that we can find stronger inductive biases for, maybe there's progress to be made that way. That's in terms of talking about deep neural networks, which I think are still lagging behind tree-based methods in that domain. And I guess seeing if that gap can actually be closed. And I know others in the group have also worked on kind of transfer learning and these sort of ideas, because I suppose that's where deep learning has its advantage. You know, transfer learning, these methods are pretty established, whereas this is not such a straightforward approach in kind of tree-based methods.
Thank you, Alan. And of course, causal graphs potentially as a inductive bias. Alicia, you had questions for our panelists as well.
Yes, I guess the first kind of just a very high level question, just out of curiosity. Obviously, we've now studied double descent, which is kind of a like phenomenon that has appeared like quite prominently in the like more theoretical literature very relatively recently. I mean, the original paper on it was, I think, published in 2019, and I think it's been cited like 2,000 times now. So there's been quite some interest in it. But I wonder, does it matter in practice? Have you seen any examples of double descent or other types of, like, let's say non-standard learning curve behavior, jumps, peaks, whatever, that actually have had any impact on your practical lives or your data scientists' practical lives?
I can maybe start replying to this. It's a great question. I mean, I would probably say that, first of all, I mean, in your papers, you're using ImageNet, which is an amazing data set. It's a very clean data set. When it comes to healthcare and all these systems, we do work also with some image or sequence data, etc., but most of it still remains tabular data, which means we don't have any context because of the space relationships or other things. And we cannot inherently model anything around this. So usually, in order to assess and validate our models, we rely on more tangible results, or like label data from, let's say, clinical trials, or like targets that have been effective eventually, or some empirical data essentially that we can trust. So that was also my previous point around the ensemble models. The different members of the models will clear out some technical artifacts, or they will provide the consensus that is supported by multiple different avenues towards the same path. It doesn't necessarily point to the optimal or to the correct path eventually, but hopefully it moves this path out. But eventually, yeah, I would probably say that it's not, unfortunately, I would probably say, part of our daily process, let's say, to keep track of a double descent or descent in the hyperparameter tuning, for instance, because this can happen with a grid search over multiple hyperparameters. However, it would be extremely useful and important if we had much more clarity about what is actually happening in the background, and have full control about the effect of this hyperparameter and whether this actually affects complexity, or is it worth doing that. And that also affects even efficiency when it comes to training the models as well.
Yeah, I can certainly agree with from the point of the tabular data, for example, your random forest XGBoost. I can't remember off the top of my head how many hyperparameters XGBoost has, but it's a high number. And having an understanding of what the difference they actually make and which ones you should focus on would be great. As currently, I think that the common approach is perhaps to do like a random grid search. As regard to kind of deep networks, unfortunately, I would say that no, I haven't observed double descent, and very often with medical imaging, you suffer from a very small number of data points. So you take ImageNet, it's tens of thousands, I think, off the top of my head, is the size of the samples you have, and they are relatively small images, 256A, 256A. Whereas we often deal with, say, CT images, whereas CT images can be 512 by 512 by, say, 300. And you often find that the size of the networks that you deal with in that case, because you're fortunate if you have a few hundred CT images, which are labeled, they're very difficult and very expensive to label. So compare that to, like you mentioned, I think you let's see, your ResNet 18 is considered to be the small size with just 18 layers. Whereas when you're dealing with image segmentation, you're often dealing with the UNet, which has just got 5 layers, would be considered a high number, 5 down and 5 up. So the size of the networks you're dealing with are actually very small compared to what you might have when you're dealing with things like ImageNets. And I'm going to use the opportunity to throw a question back at you. And I was curious that you've demonstrated in your paper that independent nets did better. Now, how would you feel then the trade-off between a large network and a few small networks? So is there not a similar argument to be made there, that you've shown that joint training of many small networks was worse than training those small networks separately? So can we not use the same argument and say, let's suppose I've got a choice here. I've got a ResNet 34, or I could do 2 ResNet 18s, and actually kind of train those completely independently. So I'm just curious to see what you think about that as well.
Yeah, maybe I can answer that one. Yeah, so I think if when it comes to when you're in the independent training, so if we're discounting joint training, right, that's off the table, that doesn't work. And the question then is, okay, should we scale a single model or form an ensemble of smaller models? And there was actually a relatively recent work from last year from a group in Colombia where they did a huge empirical study, and they actually found that performance, when you kind of matched up for compute, the performance of the deep ensemble was actually pretty similar to the performance of the larger model, which is kind of interesting. Now there might be some nuances to that. Maybe there's things a deeper model can represent that an ensemble can't. But then on the other side, the ensemble has the advantage that you can train it in parallel, which is obviously huge when there's a certain point that you just can't go any deeper on whatever your computational budget is. So yeah, there's definitely people who have looked at this question, but I think there's also further work to be done there. I think it's a great point though.
Alicia, did you have a second question you wanted to ask of Jeremy and Dimitris?
Yeah, so I'll just keep it to one more. For us, so we found the double descent like very interesting, the two of us, because we're both statisticians and we're taught that like model complexity error, there's a U-shaped curve. That's just how it is. So it didn't sit, this like very counterintuitive finding of like double descent didn't sit well with us. So that's how we kind of looked into it. I was wondering if there's anything not necessarily related to double descent or so, but any kind of machine learning phenomena that you've observed in practice that don't sit well with the intuition of what should have happened for you. Anything you've observed in practice overall that really that you've thought, oh, someone should look into this. I don't understand why this is happening.
I'll come in first because I'll grab the obvious one. It's large language models. It's like I'm sort of really looking forward to your discussions on those. Just talk for example of emergent behavior and are they actually doing reasoning or not? And I've had to eat my hat on the capability of large language models, I must confess, but I am really kind of fascinated to kind of see kind of are they actually doing reasoning, and that's a really a key question for me.
Maybe
Two
from my
sessions
point
on large language models next, so it's a good question for the next two sessions.
Yes, from my point of view, I would probably say I'm getting surprised quite often with the performance of ensemble members in similar settings. And this might have to do with the degree of confidence that we may have on the tabular data that we're using. So what I mean by that is that with image data, I mean, we have some fairly clean values, I mean, for each pixel across some channels, etc. With tabular data in life sciences, we need to collate data from multiple different resources, compiled by very different labs and groups or different modalities, eventually crammed into numerical representation or a categorical variable. And then it's surprising how in the same ensemble classifier, different types of models will perform slightly better for some, let's say, diseases, which is like a subset of the entire problem space where this ensemble classifier is applied to. And that might be interesting to explore as an extra avenue to see whether it's the degree of confidence that we have in the original data that drives a better or worse performance of some classifiers in some cases. That could be like an exploratory project, of course, and combining, I mean, more traditional machine learning models and deep learning models and see whether there's an impact of the quality, essentially, of the tabular data for each member of the ensemble.
Amazing.
So
Thank you.
kind
Thanks
of
for those two
almost a
questions.
relationship between data-centric AI, which is an area dear to our heart, and the area of machine learning in general, of deep learning and of foundations of machine learning.
Thanks for those two questions, Alicia, and thanks, Dimitris and Jeremy, for those answers. I think there's a lot for us to think about there as well. I saw a couple of questions from the audience that I'm going to try and take in the time we've got remaining. The first one was from Elena. So Elena, do you want to unmute yourself and ask your question? I think this one is for Alan.
Sure, that's right. Thank you so much for the wonderful talk and event. I just was wondering, sort of, if you have a deep learning model and there's really no change that sort of one has applied to data or training or anything, then it's expected that sort of it's not really learning any kind of new information. And so is it what can be done to make kind of the model not collude?
Yeah, so I think what was quite a surprising finding in the deep learning setting is so for a bit of context, I guess what you're kind of nodding towards is that, you know, when we're training decision trees, we do things like bootstrapping, where each model is seeing different subsets of the data set. And when it comes to the deep learning regime, the only difference between the different members of the ensemble when we're training them independently is that they have a different random initialization in their parameters, and they see when it comes to independent training, they see a different kind of ordering of the data as they train. And I think at least to me, what was surprising about that is the level of diversity that gives you among the solutions that you eventually arrive at in the loss landscape. It actually seems that this turns out to be kind of sufficient diversity. And there has, I think, a lot of ensemble research has in the deep learning regime has kind of focused on this diversity aspect and has looked at increasing diversity. And I think the big takeaway that I've seen has been that actually we don't need a higher level of diversity in among the ensemble members. This seems to be enough. And I think kind of the research community, I think, needs to kind of internalize that message and kind of focus on different aspects. Yeah, and I think this is kind of highlighted by facts like I know there was a paper that looked at bootstrapping deep ensembles, so subsetting data there, and this just doesn't, this actually makes things worse. So yeah, there seems to be something kind of fundamentally different about these high capacity models than low capacity models in terms of diversity. Thanks for the question.
Thanks, Helena, and thanks, Alan, for answering it. I think we've got time just for one more quick question, so I'm going to invite Rhea. I think, Rhea, you've got a question for maybe Alicia to take on the double descent talk. Do you want to unmute yourself and ask your question? Oh, I'm not sure that they're still here. Maybe I'll read out their question. So thank you for the session. I'm curious how moving the peaks and architectural variations of double descent can be applied to designing models, optimizing the number of parameters, or is this instead a lens to get a statistical intuition for existing models?
Yeah, very interesting question. Too bad the asker is maybe not here anymore. But so like one thing that we took away from these results is that what the shape of the effective parameter curves tell you is that these big models, as you move along on the second axis, make smoother and smoother predictions, despite the fact that they can still interpolate. So it seems that for the data sets that we considered, having models that make smooth predictions, that's really the inductive bias that works really well in this data. So that one could take away simply and say, okay, smoothness regularization, so ensembling, L2 regularization, these kind of things do seem to work very well in this data, and that's like having the models be smoother is exactly what causes the second descent. And then, so this is something I hinted at in the presentation. We actually did some experiments with gradient boosting in our appendix, where we chose between different hyperparameter settings of like other hyperparameters simply by like we trained all the models to zero training error, and then just pick the models that are smoothest. So the ones that use least effective parameters while still being able to interpolate the training data, and that works quite well as that on these data sets work quite well as a strategy. So I think there's something to be said there about that selecting models that make smooth predictions is generally a good inductive bias. And I think that is very much in line with standard statistical intuition. I think what speaks a little bit against the traditional intuition is that actually it's possible to perfectly fit the training data, yet still be able to be smooth on new testing data, is I think that's kind of the counterintuitive finding. But yeah, so this kind of smoothness inductive bias can definitely be taken into the design of new models, with the caveat that this is very much an empirical observation. Like we just observed that the smooth models do seem to work quite well in practice, but I think that has to do with how the data is actually, like what the actual data generating processes are. So if the true underlying functions are not very smooth, maybe this doesn't work so well. But I think in practice, I think we often assume that there's some kind of smoothness in outcomes, that you have, like if you have your patient's characteristics, that outcomes don't jump very, very like non-continuously. So yeah, so kind of what we took away is smoothness seems to work quite well in practice.
Thanks, Alicia. I think now we're just approaching the end of the session, so I'm just going to quickly wrap up and say that if you enjoyed the session, it's going to be on YouTube soon. So if you have any friends or colleagues that you think would also enjoy it, please do share it with them when it's available. And we hope to see many of you back for our next 2 sessions that will both be about this emerging field of large language models. And this will be on the 15th of February and then the 11th of March. Just like to thank both of our speakers, Alan and Alicia, once more, and then our 2 panelists, Jeremy and Dimitris, for joining us today. I hope you enjoyed their conversation as much as I did. And I look forward to seeing as many of you as possible for our next session on the 15th of February. Thank you very much, everybody.